Okay, welcome to lecture. Welcome to lecture, and we are going to pick up where we left off with his chapter 11. So I think right about here is where we left off last time. Again, as always, if you have questions on anything, feel free to type them there in the box. And again, we'll get to them. Even if we've moved past it, we'll come back and get to it. All right. So last time we were talking about really saturated, hydrocarbons like alkenes and alkynes. Remember, alkenes have double bonds, a carbon-carbon double bond, while alkynes have that carbon-carbon triple bond that is happening. And a result of sort of that carbon-carbon double bond is a certain type of isomer, which are known as cis or trans isomers that we talked about. And cis essentially means the same side of the double bond. So you have a group that's going to be on the same side of the double bond, while trans is basically opposite. So cis is the same, and trans is opposite side of the double bond. Remember, we talked about a couple of things in terms of how to identify them, a couple important things to make sure of when you're looking at these guys to determine if it is a cis or a trans isomer, or even if it is possible to have a cis or trans isomer. And some of the important aspects of it is it's always around that double bond where you're concerned with. So it's always where that carbon double bond is. And remember that when we look on the same carbon, we need to have different groups. And on both of these carbons, again, we need to have sort of different groups attached. But there does need to be a group on opposite carbons that are the same. And again, it's really where those groups are at. Is it on the same side of that double bond, opposite sides of the double bond, that allows you to determine whether or not it's going to be cis or trans. Remember, though, if you do have a double bond where on the same carbon you have the same group, and a group could be nothing more than a hydrogen in this case. Again, same group on the same carbon in the double bond, that automatically basically prohibits the cis or trans isomers from occurring. So let's take a look at some of these here and try to determine whether or not these are cis or trans, and then we can talk about sort of the naming in a bit here. But let's just take a look at the first one here. So again, we want to focus in on that double bond, and that double bond there has one group here and this group, which are different, so that's good. This group here and this group here are different, so that is good. And now when we look across the double bond, these two groups are the same, and really you could look at the hydrogens as well if you want. So these are on the same side of the double bond, so this would be the cis isomer here. Same thing here, if we look at our double bond on our second one, again, that's the important carbon-carbon relationship. And we have different groups here. We also have different groups on the right-hand side, which is good. And now, again, if we want to look at the CH3 group, these guys are the same on opposite carbons, and they're also on opposite sides of the double bond. So this guy would be the trans isomer. And lastly here, if we look over here, again, the double bond's the important. We have a different group here and here, which is good. We have a chlorine here and we have a chlorine here. The problem, though, is that is the same. Yeah? And because that is the same, you can have neither cis or trans. Yeah? So remember, they must have different groups on the carbons, same carbon, and a group that's the same. Now, also remember that although it may be drawn this way to illustrate the cis or the trans, when you are going to name it, you still want to kind of follow the same stuff we talked about. So, for example, if we did longest continuous carbon chain, that's 1 carbon, that's 2 carbons, that's 3 carbons, and that's actually 4 carbons in that. Although, again, as we talked about last time, people oftentimes will focus in on that double bond. So 4 carbons, that's based off of butane. It has a double bond, so butane becomes butene. And the double bond is located at carbon number 2, no matter which way you go. That's 2-butene. And again, we would put the trans in front of it, although most people don't do a dash. They could just kind of write trans, 2-butene. Same thing if we went over here. In this case, actually, the longest continuous carbon chain is these 2 right here. And that's it in terms of carbons. And that would be 2 carbons based off of ethane. Again, we have a double bond, so that becomes ethene. And in this case, it is 1, 2, because it doesn't matter which way you go. That's 1 and that's 2, or that's 1 and that's 2 going the other way. And that'll be 1,2 dibromo. I'll try to squeeze it in. Ethene, and we would put the cis in front of it as well. So that'd be cis 1,2 dibromo ethene. Again, with the halogens named that way: chloral, bromo, fluoral, iodo. And this guy again would not be a cis or trans. So longest carbon chain here would actually be 1, 2, and 3, which is based off of propane. We have that double bond making it propene. And really, you kind of don't need it, but we'll use it anyways. We'll call it 1-propene. And the chlorine here would be off of that first carbon going this way. And this would get us 1,1-dichloral. Oops. 1-propene. I got an extra little comma in there. Get rid of that. And so forth. All right, any questions on how to identify cis or trans isomers here? Okay, so remember, you may, like the bottom one here, not be able to do it. And again, that occurs because there's the same group on the same carbon. So what we're going to talk about next is basically the reactions that these alkenes undergo. And these type of reactions are what are referred to as addition reactions. And these are different than the substitution reactions that we talked about with the alkanes. Remember, in a substitution reaction, we took off a hydrogen and put something else on in its place. In an addition reaction, what we do is basically add 2 things. And what we add 2 things to is always, much like the picture on the bottom sort of shows, it is always to the double bond. So for example, if we added Br2, which would be 2 of these, right? Br2. Now, in an addition reaction, there's always a thing that happens. So for example, if I wanted to put a bromine onto each of the carbons, which is what's going to happen, and if I just throw the bromine on just like this without doing anything else, the one thing that you should hopefully be able to see at this point is each of these carbons now have 1, 2, 3, 4, and 5 bonds, which is way too many bonds for carbon. Remember, the whole point of carbon is it should only have 4 bonds. So we don't really have room for those bromines to add on to each of the carbons the way it is. So we essentially need to make room for it. So what always happens in this type of reactions, this addition reaction, is we always make room for the whatever's coming in by turning this double bond right here becomes all the way over, a single bond. Yeah. So that's what you should remember when you're doing these type of reactions. the double bond becomes a single bond. And as we talked about with reactions, nothing weird happens, nothing crazy happens. It will look exactly like it does there on the left. The only difference is it will become a single bond. So that's what I was saying before, that you essentially have almost the answer for you, because you could just copy what is on the left-hand side, for example. And you can see that the only thing I did was turn that double bond into a single bond. Now, because this is an addition reaction, what's going to happen is one of these guys over here will go to one carbon, the other guy will go to the other carbon. And we could do that now because we made room for it by making that a single bond. And we would just add one to both sides there. You don't need the underline. And that would give us our new product here. So the general thing that happens in this type of reaction when we do an addition reaction is pretty much a double bond becomes a single bond. And then you add one atom to each carbon. And this type of addition reaction that we just did right there on the top is what is referred to sometimes as a symmetrical addition. And what that means is we are essentially adding the exact same thing. So in the case above, we're adding a Br to each of the carbons. You really can't screw that up because it's the same thing. So you could put one Br on the left, one on the right. It doesn't really matter because you're essentially adding the same thing. So one type of addition reaction is what is known as a hydrogenation reaction. Hydrogenation reaction means we are adding hydrogen to each of them. Same thing is going to happen here. Absolutely nothing else is going to change. Nothing else is going to change except for that carbon-carbon double bond will become a single bond. Whatever else is attached there, again, you would draw it exactly the same. And then one H there, and you would be done. Let's see, CH2Br, Br on that one. Probably if you were going to write it in more of a condensed form, which I think might be what you're asking, you probably would still do it more like this. And then maybe just show the bromines kind of like that. Again, sometimes you don't want to run everything sort of in a row when you're doing condensed, especially those groups that are sort of attached to the longest carbon chain. You kind of want to maybe kind of differentiate them by maybe just writing those out kind of separately. So usually this type of reaction will take some type of catalyst to speed it up. So you'll sometimes see on the arrow something written there like palladium, UV, something like that. And this is, again, what is known as a hydrogenation. We go from an alkene, and because we make that double bond into a single bond, we go from an alkene to an alkane. And we basically just add H to it. This is also a symmetrical addition. Again, we're adding the exact same thing. Can't really mess it up. One H to one carbon, one H to the other carbon, and you would be fine. Again, absolutely nothing else changes in the molecule other than that one little spot. So here again is an example. And again, if you look at this, as we go from left to right, the only thing you should focus in on is right here. Again, you should draw everything just like you find it. Again, making the double bond into a single bond. And in this case, we are adding H2, which is two H's, one to this hydrogen. I'll just put a circle around it. You don't have to, just to identify that's the one we added. And as hydrogen on this one as well, as that's the one that we added. Again, you don't usually put circles around it, but just to show you that's where the current of the hydrogens came on. And again, you can kind of think about, as we talked about, in order to make a bond, we have to lose 2 hydrogens. So in order to kind of make room for a bond, we have to kind of, take out that double bond, and that leaves room for 2 things to come in. So why don't you try drawing the products of each of these? So take a moment or two and draw the products of each of these reactions here. The purpose of hydrogenation is one way that you can make an alkane. We'll actually talk about it later on in, not sure what chapter that is, maybe 15. This is actually when you, for example, when you hear something is partially hydrogenated, for example, like how you make margarine and stuff like that. That's sort of the process where they get rid of some of these double bonds and make them single bonds, and it actually changes some of the properties of the compound. And that's sort of how we sort of get things like, for example, margarine and things like that. And again, when you hear somebody says it's partially hydrogenated, it's basically this reaction here. All right, so when you are asked to draw these sort of products, remember they are actually not as hard in a lot of cases as you may think. It does sometimes end up being hard for people because, again, everybody wants to do a whole bunch of weird things that you should not do. So you want to just keep it simple. And all these reactions we're going to be talking about, they really all basically will have only one part of the molecule that is basically involved. So what I'm going to do is I'm just going to redraw this top one here kind of out with everybody drawn out with their hydrogens and everybody so you can see everything. And again, I'm just, like I said, kind of doing the expanded structure here so we can focus in on everything that we need. So we're basically taking this guy plus H2, which is this. So again, once you see that double bond, that is the functional group. That is the important part. That is essentially where you should put your focus on, is right there. And what you should know is what we were just talking about, that everything's going to be exactly the same. There's nothing that's going to change on that molecule on the left other than we should make the double bond into a single bond. So you could literally very quickly draw it exactly the way you have it on the other side. Again, just making that double bond into a single bond, and you will end up with something that looks like this. And now, once we've turned that double bond into a single bond, we now have room for our hydrogens to come on. And again, they come on one at a time into separate hydrogens. So we would separate carbons, we'll get a hydrogen there. and we would get a hydrogen there. Yeah, so let's make this guy red so we can kind of follow. And that would be it. There it is. We go from an alkene to an alkane. And like I said, sort of a practical aspect of it is something like that. You know, that's again what it means when we talk about something being partially hydrogenated and those type of things. And again, you can hopefully see that absolutely nothing has changed other than the part that was the double bond. Now, when we come down here, same deal. Again, this is line structure. Remember, if you count the lines coming into our carbon, this carbon right here has a hydrogen there. This carbon right here also has a hydrogen. The rest of them have 2 hydrogens all the way around. Now, again, when we focus in on this thing, it is just right here, that carbon-carbon double bond that's going to change. And again, this is where people also like to, you know, kind of do weird things. This guy is not going to open up and become straight or anything like that, like a straight chain. It's going to remain the same. So you would draw this guy exactly the way you see it on the other side, maybe a little better than I'm doing here. Ish. Again, we're going to turn this double bond here into a single bond. We have a hydrogen that's going to go to each of these carbons here. So this will get a hydrogen. This guy will get a hydrogen. And that will go with our original hydrogens that technically were there as well. So remember that we had a sort of red hydrogen, if you will. That was already there. And a red hydrogen that was there as well. So it will look like that. Again, because it's technically hydrogen, most people would probably just draw this like so with nothing else written there. Again, assuming that everybody there is a hydrogen. Any questions on that? So hydrogenation, which is a symmetrical addition reaction, essentially draw everything exactly the same, turn the double bond into a single bond, and then you can add 1 hydrogen to one and 1 hydrogen to another. Any questions on that one? Let's see. To be too honest, if you're asking about this bottom one, truthfully, because this one is usually written as sort of a line structure, most people would just draw it like on the right there, because drawing it like that implies that those hydrogens are there. Maybe if you're doing a sort of chemical equation like this, you might want to just to accentuate that those 2 hydrogens were added, maybe just draw the 2 hydrogens like this. You know, technically any 3 of these guys are okay. Again, most people would probably just draw this picture or this picture here. Again, maybe just to accentuate that the hydrogens there. Because technically, again, this is more of a line structure, the bottom one, and we typically don't draw the hydrogens in line structures and stuff like that. So probably most of the time somebody would do the one on the right. Now, the one on top, which is more of a condensed formula, you know, people would probably either write it like I did there on top, which is really not a condensed formula, or they may just convert it into, you know, CH3, CH2, CH2, and CH3. Again, that's another way that you could do this guy here without drawing it completely out. So again, that would be more of a condensed structure. The one where I drew out all the hydrogens would be more of a expanded structural formula. Any other questions on that? Okay. Now, that was a hydrogenation. Again, you could add a bromine like we did, which is a symmetrical addition. Now we're going to talk about some reactions here, which are what are referred to as unsymmetrical. And an unsymmetrical addition reaction, unlike where we had, say, the two hydrogens that we added, you know, the two bromines, like the first example that we did. This again is symmetrical because what we are adding is exactly the same to both carbons. So you can't mess it up. One gets a bromine, basically the other gets a bromine, which again is your symmetrical addition. Now, when we add something that is two different things, like water, for example, which is what the above reaction is here. When we add water and we're doing these type of reactions, we sometimes think of water in this form, like they have it as we're adding an H and an OH. So the overall reaction is essentially the same. You're going to do the exact same sort of setup. You're going to take your carbon-carbon double bond. You're going to add water to it, which again you could think of as H and OH. And the exact same thing is going to happen. We'll go all the way over here to get a little bit more room. We're going to draw this guy exactly the same. And the only thing that's going to change here is the carbon-carbon double bond will become a single bond. So we would draw it just like we did with the other one, exactly the same, making that double bond into a single bond. And again, that is going to create an opening now for the H and the OH to add. And again, this is what is referred to as an unsymmetrical addition, because in this case, one of the carbons will get the OH and the other carbon will get the hydrogen. So again, hydrogen and OH. And this reaction here is what's referred to as a hydration reaction because we're adding water. And in this reaction, this is a way that we can make a alcohol. Remember, an alcohol has a functional group of OH, which is right here. And we go from an alkene in this case to an alcohol. In this particular case, it doesn't really matter which way we add it. If I put the OH on the left-hand side and the H on the right-hand side, you get the exact same molecule. That is both what is known as ethanol, is what this guy is. Ethanol. From ethane to ethanol, basically, through this hydration reaction. Now, there sometimes is a case where it does make a difference in terms of which one gets the hydrogen. And there is sort of a rule, which we'll talk about in just a second. Let's take a look at the next one here. This usually happens with a strong acid, and that's what this is here. This, again, is just here to act as a catalyst, if you will. So sometimes people will see this up on top. Sometimes they'll put H plus on top to indicate there's an acid. This will have no effect on the product being made. So that's also something sometimes people will do, is we'll try to incorporate that sort of catalyst into the product. Remember, a catalyst is just there to make the reaction occur faster. So don't try to incorporate it into anything. So here's that reaction that I just did. And this is, again, an unsymmetrical addition sort of reaction. Now, in this case, when we look at this guy here, and again, that last one was the one we just did up on top. When we look at this one here, there is a couple of options when we look at what we're starting with here. So when we start with this guy here, we're still going to add an H to one carbon and an OH to another. And when we kind of break this guy apart and turn that double bond into a single bond, when we add that H and OH, you actually have a couple of options in terms of which one goes to where. One way you could do it is like what we see on the right there. You could put the H coming in from the water on the right. You could put the OH coming in from the water on the left, or vice versa. You could put the OH on the right-hand side and the H on the other side. And if you do that without drawing a line up there. And again, we could do the OH over here and the H over here. And in this particular case, the difference is we actually can get two different products that are formed. These are both alcohols. One, as you can see up here, has a name of 2-propanol, which is one type of alcohol. This is what is known as 1-propanol. By the way, it is named because this has 1, 2, and 3 carbons, which is based off of propane. The OH makes it an alcohol, so we drop the last part and it becomes propanol, OL, like an alcohol. And the 1 is for the location over that OH group is located in that case. So this gives us what is known as a major product and a minor product. And there is a rule that you should follow in these unsymmetrical additions, and it occurs when you add something like, for example, water. It occurs when you add something like HCl, HBr, you know, two different things being added. And if there's an option like here that it does make two different compounds when we add it, the rule that you follow is what's known as Markovnikov's rule. And Markovnikov's rule is that the hydrogen is going to go to the carbon that started with the most hydrogens. So what that means is, I'll get your question in just a sec. When we look at these carbons, attached directly to the carbon on the left-hand side is one hydrogen, right? And that would be this guy right here. When we look at the carbon on the right-hand side, attached to that carbon is two hydrogens. One here and one here. So when this hydrogen comes in, it is going to end up at the carbon that had the most hydrogens to begin with, which as you can see is the right-hand side. And that's why this is really what is referred to as the major product. While the minor product would be the opposite, where we add the hydrogen to the other carbon. And this is what is sometimes referred to as the minor product. Now, in certain cases, when you do this unsymmetrical addition, it does result in two possible products, a major and a minor product. And the major one is always the one where the hydrogen ends up on the carbon that had the most hydrogen. Now, if you look back at the one we did previously to this particular one, this carbon here has two hydrogens. This carbon here has two hydrogens. This does not matter. Again, you could do it like this. You could do it the opposite way. It will still give you the same product regardless. It is only when you have sort of this option where you can basically make two different products that you always want to put the hydrogen on the one with the most to begin with. Any questions on that there? All right. So let's take a look here. And that was the guy's name that I was butchering really badly. That rule where we put the hydrogen coming in on the one with the most hydrogens is what's known as Markovnikov's rule. And that's basically what it says here. Add the hydrogen to the carbon that started with the most hydrogens attached directly to it. So it has to be the hydrogens attached directly to that carbon is what we're talking about. So again, that was our example here that we saw when we counted our hydrogens. I'll just kind of let that scroll on the screen, but that's essentially the one we just did. All right, so why don't you take a couple minutes here and draw the products of each of these. There you go, the bottom guy in. All right, so draw the products of each of these. All right, so let's take a look here and sort of see each of these. So again, when you're doing these and you're asked to draw sort of the products, you don't want to overcomplicate it or anything like that. And again, the answer is sort of right there most of the time. Just to so you can clearly maybe see what's going on, I'm just going to redraw the first guy with all the bonds out so you can again see sort of where everything is. You don't necessarily have to do this, but just want to kind of show you. So probably want to do it right here. And of course I double bonded. It's a good thing they make erasers, I suppose. All right. There we go. Okay, so this is an H. That's my double bond that way. And another carbon and an H. And CH2. see if I can get my mind and my hand working here together correctly. And one more. There we go. All right. And again, we're adding H2, not H2, H2O, which is essentially H and OH in this case. So again, although it is kind of a big kind of guy, as we talked about before, it is only right here that's going to change. And the way it's going to change is, as we talked about, we're going to turn that double bond into a single bond. And again, everything else that is there, you could draw exactly the same way. So I'm just going to copy exactly what's there. Again, don't do anything weird like changing bonds or anything like that, adding weird things in there. Again, the only major change is right here. Double bond becomes a single bond. And I go an H and an H. And then we have everything else exactly the same going down this way as well. So again, everything going to be exactly the same as it was before. The only difference, turning that double bond into a single bond. Now, in this particular case, this carbon here has one hydrogen attached directly to it. This carbon here has one hydrogen attached directly to it. So in this particular case, you could put one hydrogen on this side and one OH on this side. Or if you flipped it around, you actually would get the exact same molecule. And it would be, just so you're curious, it's an alcohol. This alcohol has 6 carbons. 6 carbons is based off of hexane. It's an alcohol. It becomes hexanol, OL. And the OH group, which gets the priority, would be at carbon number 1, 2, 3. And this would be 3-hexanol, which is what we would actually end up getting. But more importantly for us right now, double bond to a single bond. H goes to one carbon, OH goes to the other. And again, in this particular case, you don't have to choose one over the other, again, because they have the same number of hydrogens to begin with. All right, any questions on that one there? All right, so let's take a look at the next one. And next one, same deal. Again, you don't have to redraw it, but I'm just going to do it here so you can kind of see everything that's going on. And again, keep track of everything. So we'll look like this. This I'm not going to draw. I'm just going to keep that condensed. And we got our double bond this way. And we got this. And we got this. And again, we're adding our water, which is H and OH. So again, when we focus in on the original guy, nothing's going to change but where that carbon-carbon double bond is, which is right there. Everybody's going to be exactly the same. So again, you could redraw it exactly the same for that second one. The only thing we're going to do is turn that double bond into a single bond. And again, everything stays the same. So we still have our CH3 group there. We also still have our hydrogen. Now, though, when we look at each of these carbons in this bond, this carbon has one hydrogen attached. This carbon has 0 hydrogens. Yeah? In this case, it does make a difference in terms of which one gets the hydrogen and which one gets the OH. And again, based on the rule, the hydrogen will go to the carbon that had the most hydrogen to begin with. So the major product, which you should always draw, will look like this: hydrogen to that carbon and OH to this carbon here. And again, This will give us our major product, which is 1, 2, 3, 4, 5 pentanol. And this would then be 2-pentanol, would be the name of this alcohol here. By the way, it would be 2-pentanol. 2 because of the location of that. And this would be the major product that you would draw. The minor product would be the opposite. So the minor product would have these two guys basically switched around. But again, you usually want to draw the major product when you do it. Any questions on that? So again, that Markovnikov's rule, hydrogen goes to the one that started with the most hydrogen, and the OH would go to the other group. All right, and lastly here, if we look at this guy, just like before, it is going to be right here, the double bond. This carbon has a hydrogen. This carbon has a hydrogen. Yes, thank you. I totally missed the methyl group there. Thank you very much. It would be 2-methyl. Thank you. You are correct. Everything was blending together. Thank you. It was hiding right there. That is correct. It would be 2-methyl, 2-pentanol. Thank you. So here would be, we would take that double bond just like we did previously and just turn it into a single bond. And in this case, both of those would have a hydrogen, and they both have one, so it doesn't matter which one you do. You put the hydrogen to this carbon and the OH to this carbon, and that is based off of cyclopentane. Because it's an alcohol, it then will become cyclopentanol, OL, at the end of it. And that would give us our alcohol. Yes, thank you very much on that top one. It should have definitely that methyl group there. I just sort of missed them in all the writing that was there. Question on these sort of unsymmetrical additions. Now, all these examples involved water, H, and OH, but you could have done any of these with H and something else like Cl or Br. It works the same way. Hydrogen would go to the one that has the most, if there's an option, and then the other guy would go to the other one as well. Any questions on that? All right. So you got a couple of these here. So give these a go, see what you come up with. So draw the products here. All right, so let's take a look at these and see how we're doing. So again, when you're doing anything with a double bond here, we're adding two things to it, always going to be an addition reaction. So again, only this part of the molecule where that carbon-carbon double bond is going to change. And again, we're just going to simply draw it exactly the way it is. Let's draw it down here. We're going to turn the double bond into a single bond. Absolutely, positively, nothing else changes in this case. Now, in this case, we're adding H2, which is a symmetrical addition. Again, you can't mess it up. You pretty much just need to put a hydrogen on each carbon, and you would be good in terms of the first one there. I know I kind of drew it like that. You could draw it straight up like this as well. You know, it's all good. The nickel here, again, on top of the arrow is not going to do anything involved. It's just a catalyst here, again, just to speed up that reaction. Again, if we go to our number B here, it is only the carbon-carbon double bond that's going to change. So again, you could draw this. I'll draw it here since maybe we're running out a little bit of room. We're going to draw it exactly the same. We're just going to turn that into a single bond. And I'm just going to write everything the same for now. And I got one CH3 hanging off over here. Now in this case, though, we are adding water, which is H and OH. So we do want to look at each of the carbons there in that double bond to begin with. And if we look at the carbon on the left-hand side, it has no hydrogens, 0 hydrogens. We look at the carbon on the right-hand side, directly attached to it is 1 hydrogen. So that's going to be important in terms of when we add the H and the OH, because the H should end up at the carbon that had the most to begin with, which in this case would be this guy. And the OH should end up at the other carbon, which would be that guy right there. And again, that would get you your major product in terms of what would be added. Any questions on those two right there? Again, same deal as we go here to the left. We got just the carbon-carbon double bond. That's the important thing. As I butcher the way that looks now. And we're just going to copy it exactly the same if you can still see it. We're going to turn the double bond into a single bond. And in this case, though, we are adding a symmetrical addition. It is Br to each carbon. So again, it does not matter which one you put it on, because it's basically the same thing on each of them. And we would end up with that guy. And lastly, over here, we're going to focus in on the carbon-carbon double bond there, which means although there's a lot of other stuff kind of flying around, it's all going to be the same. We're not going to change it or do anything weird with it other than making that into a single bond. Now, this one is not water. It's not two of the same things, but it works just like water. We're adding an H and a Cl in this case. And the same rule applies. We want to put the H on the one that has the most hydrogens to begin with, if there is an option for that. So when we look at this carbon, it has 1 hydrogen. When we look at this carbon, it has 2 hydrogens. That means that this carbon on the right technically should be the one that gets the hydrogen. So that is where we would add the hydrogen in. And we would put it over here, wherever you went. There we are. We'll put the hydrogen there, which basically gives you a CH3 group, but I'll just draw it out so you can see it. And this would be a Cl in this case. And we'll end up with basically that. Again, the guy on the right there, most people would probably just write CH3 at the end, but I'll just kind of draw it out there. Your question is, do the BRs have to be on the same size? Are you talking about here, like I put both of these guys on the same side? You could if you wanted to, instead of drawing the one I'm circling up on top, you could have drew them on the bottom. It's perfectly fine. Again, because it goes back to an alkane with that single bond, so they're free to kind of rotate around technically. And so you could have drew this BR on the bottom if you wanted to, and did that one on top. It wouldn't have mattered in that case. Other questions or questions on how to do these addition reactions? So symmetrical addition reactions. Symmetrical addition reactions, you can't really mess it up. You just want to follow double bond to single bond, one on one carbon, one on the other that you're adding. Again, it's just the unsymmetrical additions where if you're adding hydrogen and OH or hydrogen and Cl or hydrogen and Br, if there is an option like we had in a couple of these where there are more hydrogens on one carbon to begin with than the other, then always the hydrogen to the one that is has the most hydrogens to begin with. The names for what we ended up with in terms of our products, I could perhaps. Let's see. So I guess I should use the eraser to do that with here. So if we start on here in terms of the products, I'm assuming that's what you're asking. This is 1, 2, 3, and 4 carbons, and nothing else there. So that's just butane. Again, going from an alkene to an alkane. Will come, that was the same one. So we ended up over here. Longest carbon chain here is we got 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons if you go that way. So it looks like 4 carbons no matter which way you go. So that also is going to be butane as the base. We have 2 bromines, so that's going to be a dibromal. We also have a methyl over here, right? So probably we could go 2, 3. So this would be carbon 1, 2, 3, and 4 in that case. And in that case, that would give us 2, 3 dibromal, and that would also give us a 2 for the methyl, as opposed to if we went the other way, we would end up with a 3 for the methyl. So alphabetical there would be something like 2, 3 dibromal, 2, running out of room, we'll go this way, 2 methyl butane in that particular case. This guy would be 1, 2, 3, 4, 5, 6 carbons was like the most. 1, 2, 3, 4, 5, 6. And that's going to give us 6 carbons, which is based off a hexane. It becomes hexanol because it's an alcohol. The OH group is at carbon number 1 and 2 because it would get the priority. So that would be 2 hexanol. And then we also have the methyl group, which I won't miss hopefully this time, which would be something like 2 methyl, 2 hexanol. Again, how we would name that alcohol. And then lastly, down here, it looks like we got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So it looks like 4 is the big group there. That again is going to be butane. In this case, we have a 1, 2, and 3, or 2 and 3. Alphabetical, the Cl would probably come first. So going numbering this way, 1, 2, 3, and 4. And that would give you something like 2 chloral, 3 methyl. Always running out of room with my methyl. We'll go above it. Butane in that particular case. Any questions on that? So again, on some of these, like this last one, the numbering of the groups would end up the same regardless of which way you went. So then we would default to alphabetical, trying to put the chlorine first. Other questions on how to do these reactions here? Okay. So let's then talk about aromatic compounds. Aromatic compounds will contain the benzene ring. And again, this is our benzene ring. It's basically a 6-carbon ring that has 6 hydrogens attached. Because it has the 3 double bonds, each of the carbons will have the hydrogens. And because it has basically 1, 2, 3 electron pairs and 1, 2, 3 bonds, it will give us that trigonal planar geometry, which is 120 degrees. And again, the benzene ring will have is basically a class of organic compounds which are considered, I didn't mean to cross it out, kind of trying to circle it there. Aromatic compounds will contain this benzene ring in it. And again, that's another way you see benzene on the left, more structural formula, but a lot of times, as we talked about, people will draw sort of the benzene ring with the little circle around it as well. So these aromatic guys that contain these benzenes will somewhere have a benzene as sort of part of it. They have physical properties similar to hydrocarbons because they're all carbons and hydrogens and nothing else attached there. So pretty non-polar as well, again, because it's just carbons and hydrogens. Here's a couple of compounds, some drugs that have, obviously, as you can see, a lot of benzene rings attached in it. Now, when we do have one group that's basically attached to the benzene ring, we will sometimes just name it by that group. So again, the major thing here would be our benzene ring. And this is our 2-carbon group, which is our ethyl group. So we just call it ethyl benzene. Again, because this is the only group attached, you don't need to number it. It's assumed that this would be carbon number 1 where that group is attached. Same thing here. The major part is our benzene ring. This is a 1, 2, 3, 4 carbon group, which is based off of butane, and that's a butyl group, and that would be called butyl benzene. Here again is a benzene ring that has only 1 chlorine attached, again assumed to be carbon number 1 over there where that carbon is, and we would call it chloral benzene. So when you have a monosubstituted ring, monosubstituted means 1 group attached to a benzene ring, you essentially just named a group like normal and you just put benzene at the end of it. So that's how again we get to ethyl benzene, butyl benzene, and chloral benzene in this particular case. Now, some of these guys have sort of historical names. And even though they are benzene attached to it, they still go by these historical names. And these are 3 here that you should be aware of. Again, each of these have a benzene group attached to it and another group attached. So for example, the first one there has a methyl group attached, and you could call it methylbenzene, but it has an historical name that if you have a benzene group or benzene ring with a methyl group on it, it is very commonly known as toluene. So again, this is sort of a historical name and it is used a lot. So toluene you should be familiar with. This is also a sort of historical sort of benzene sort of ring with a group attached. This is what is known as phenol. It's an alcohol that has a benzene group on it. And this is also could be called hydroxy benzene, again for the hydroxyl group that's attached. But that's an historical name that is commonly used as well. And this one as well, a nitrogen containing group, a nitrogen with 2 hydrogens attached to benzene. That is what is sometimes referred to as aniline. So those 3 names, aniline, phenol, and toluene, you should be familiar with them as sort of their historical sort of names, because again, it is still commonly used a lot in organic chemistry, those names. So just be on the lookout for those. They tend to pop up occasionally. Now, when we do have more than one group attached to a benzene ring, we do need to give some numbering. And when we number in a ring, we want to number to give everybody the smaller numbers like normal. So in this particular case, we have a ethyl group and we also have another ethyl group here. And we would number this 1, 2, 3, 4, 5, 6. If we went the other way, like this way, we would end up with 1, 2, 3, 4, 5, 6, which would be 1 and 6, which is obviously a bigger number than 1 and 2. And we would want to go 1 and 2. And this would be 1, 2 diethyl because there's 2 ethyl groups in there. And then the big ring is benzene. So this is 1, 2 diethyl benzene. That 1, 2 location on a benzene ring also has a special name, which is known as the ortho positioning, or sometimes just O, which is what this stands for here. So if somebody says ortho diethyl benzene, that means that the ethyl groups, as we see in the picture, are at carbons 1 and 2. If we move our ethyl group one more over, going 1, 2, and 3. Again, if we went this way, we would end up with 1, 2, 3, 4, 5, 1 and 5. Again, 1 and 3 smaller. Still diethyl because there's 2 ethyl groups in here. And benzene because the whole ring is benzene. Now, the 1, 3 positioning, as you can see there, is also a historical sort of name, and that is what is known as the meta positioning, or just M, which is what this stands for. So meta diethyl benzene means that you have an ethyl group at carbon number 1 and carbon number 3. And lastly, if we moved our ethyl group one more carbon over, we would end up with 1, 2, 3, 4, 5, and 6. In this case, if we actually went the other way, we end up the same way, 1, 2, 3, 4. So 1 and 4, no matter which way you go in this particular case. And again, that's where we get our 1, 4 diethyl benzene. And the 1 and the 4 is the para positioning, RP, which is what this stands for, which means you have a group located at carbons 1 and 4. In these particular examples here, the groups are the same. They don't have to be the same. So you can't do like meta, ethyl, methyl, benzene, or something like that. So they don't have to necessarily be the same group attached. More importantly, the ortho means you have a group at carbon number 1 and carbon number 2 in the ring. Meta means you have a group at carbon number 1 and carbon number 3 on the ring. And para means you have a group at carbon number 1 and carbon number 4 on the ring. So you should be familiar with those. Any questions on that? And we would alphabetize the groups that are attached. So if we look at this here, this is 1, 2, 3, 4, 5, and 6. So it's a 1, 2 positioning, which is our ortho positioning, and then alphabetically bromol before chloral. So ortho, bromol, chloral, benzene. Here again, we would go 1, 2, 3, 4, 5, and 6, which gives us our 1, 3 positioning, which is our meta positioning. And this is meta, again, ethyl group here and floral group here. So E before F, ethyl, floral, benzene in this case. So again, sometimes people will use these historical sort of guys, ortho, para, and meta, in lieu of numbers when you have multiple groups attached to a benzene ring. Now, here's sort of an incorporation where we have multiple groups attached to a benzene, but we do hit upon one of those historical names. So up here in the box, that benzene ring with the CH3, again, as we talked about, is a historical name known as toluene. And because that CH3 is part of that historical name, that means we just have one more group attached, which is the bromol group. And again, it is a 1, 2, 3, 4 positioning, a 1 and 4 positioning, which is your para positioning. And that's what the P stands for. You don't have to give the methyl here because it's implied with this historical name that is essentially a benzene ring with a methyl group upon it. So even though we are kind of still naming it as there's two groups, and there technically is two groups attached, because that historical name toluene means that there's a methyl group, you don't additionally have to put the methyl group name in it. Same thing if we go to the right here, we got hit one of those historical groups there on the benzene ring with the OH. That is our phenol. And again, we have a chlorine attached. And that is a 1, 2 positioning, right? 1, 2, 3, 4, 5, and 6. So 1 and 2 being our ortho positioning, which is our O. Again, by using the phenol name, that implies that the OH group is part of that. So we don't have to separately sort of name it. And then the only other group would be our chloral group here. So that is orthochloral phenol. So again, it's very common, especially the toluene, the phenol, and the aniline. Those are still historical names that are very, very still commonly used for each of these. If you weren't going to kind of use this historical name, for example, something like this here, you would actually give the lower number to the bromol group, and that would be 1 bromol, 4 methyl benzene. And again, alphabetical here, B before M, which is why I gave the B are the smaller number, even though I numbered kind of the opposite way here. That would be why that would be in that case. Any questions on bromol? Any questions on para, ortho, or meta? And some of these historical names. Now, again, if we have some of these ones where we have multiple groups attached, you do want to go alphabetical around the benzene ring, giving the alphabetical guy the lower number. So again, that's sort of what I did with this last one. If I didn't use that historical name, again, I would want to give this guy the lower number because alphabetical wise, he goes first before methyl in this case. That's why technically I numbered this way, going around the circle this way when I did this name up here. And so here, if we kind of dissect this, we have a benzene ring here all the way around. And that is the base of the name. We have this guy, which is an ethyl group. We have this guy, which is a 3-carbon group, which is a propyl group. And we got that one, which is a chloral group. So we do want to number the way that will sort of give us the alphabetical order, the lowest set of numbers. Again, you really have two options. You could go 1, 2, 3, 4, 5, and 6. Or you could go the other way like they did, 1, 2, 3, 4. So you can see we would have a group at 1, 2, and 4, versus if we went the opposite way, we would have a groups at 1, 4, and 6. So this is going to give us a bigger set of numbers. So we would want to go 1, 2, and 4 to get that smaller set of numbers. And that gives us at carbon number 4, the chlorine, carbon number 1, the ethyl group, and at carbon number 2, the propyl group. Again, putting all that together would give us the whole name. Any questions on that particular guy there? So again, remember everything sort of numbering lower numbers is good. And again, I want to give everybody the smaller number. Here's another one where we have sort of that historical group in there. That's that aniline, which is that NH2 part. And if we do sort of name it that way, We then would have 2 chlorines by itself, which was the dichloryl. And since that would be sort of the base of the name, we would want to go, we could have 2 options. We could go 1, 2, 3, 4, 5, and 6. Or we could go the opposite way, 1, 2, 3, 4, 5, and 6. Going left to right gives us 1, 2, and 5, which would technically be the groups. Going the other way gives us 1, 3, and 6, which is a larger number. So again, that's why in this case we would go this way, giving us the smaller numbers. And that again gives us a chlorine at group number 2 and 5. And we don't need to worry about the NH2 group here, again, because that is wrapped up in the aniline name. So the aniline implies that there's an NH2 group attached. So if we look at these names here, since we're getting to the end, we have 1-bromol 2-ethylbenzene is sort of the formal name. Again, this would be 1, bad choice of color there, 2 going sort of counterclockwise there. Grab red maybe so we can actually see it. There we go. So again, this would be 1, this would be 2, this would be 3, 4, 5, and 6. Again, we would want the bromine to get the smaller number alphabetical. It would go first, and that gives us the 1-bromol 2-ethylbenzene. That is still the 1 and 2 positioning, which is your ortho positioning on that particular one. This would give us 1, 2, 3, 4, no matter which way you go. And that's 1,4-dichloryl for the 2 chlorines that are in there. Again, benzene. Our 1,4 positioning, again, is our para positioning, where we could call it para-dichlorobenzene. And lastly, on the far right there, we have our 1 and 3 positioning. Again, 1, 2, 3, 4, 5, and 6. And that's going to be 1 and 3, which is our meta positioning. And in this case, this whole thing here is toluene, which is the sort of basic name there, toluene. And that's why in this case, we just use nitro for that nitrogen containing group that's there at carbon number 3. Any questions on that there on benzene? Let's see what we got here. So in this box here, again, is the part that makes it toluene is that benzene ring that has the CH3 group attached, and that's that toluene part right there. Other questions on that? All right, let's see what we got going on here. A couple of things to talk about then. All right, we will stop there, I think, for today. And to answer your question, no, the exam is not going to be next Monday, I don't think. I'm going to double check when it's going to be, but I think it was scheduled for next, I want to say it was scheduled for next Wednesday, if I'm not mistaken. Right. Yeah, so that'd be a week from Wednesday, right? If I'm not mistaken on that, or maybe it was Monday. It is going to be, let me see here. It is going to be, it's already May, huh? Look at that. All right. So I think it's going to be on, it's going to be on the 11th, I think, the following week, I think, if I'm not mistaken. I'm going to double check the dates and all that, and I'll put an announcement out up on Canvas when I get a chance to look at the schedule. So we need to finish a couple more things, obviously. And I think on Wednesday, we will maybe do like a double lecture. We'll lecture during discussion as well, just to try to get on track. and all that good stuff. And so we're almost into 12, I think. So we're just a little behind. So we'll try to catch up, but I don't think the exam definitely is not going to be for when it was scheduled on the original syllabus. It will probably move, I think, to the following week, if I'm not mistaken. I will definitely put an announcement up online. We definitely want to try to get through all this stuff and all this good things. No worries. Yeah, so the test traditionally is chapter 8 and all the organics. So we at least want to try to get through most of the organics. So we'll see sort of where we're at, but I'll definitely put an announcement and let you know. A couple other things here. We'll take a break and I'll open up discussion if you have questions and stuff like that. Your lab instructor, I see, has emailed me something about the videos. So during this break, I'm going to try to put it up on Canvas, her announcement as to which videos I think maybe that you should be watching this week. So make sure you look out for that in just a second. I just got an email right before I think we started lecturing and stuff. So I can go read it and then I'll try to put it up on Canvas right now so you'll have an idea in terms of the lab part. And then, like I said, maybe about 10-15 minutes, I'll open up the discussion part. And I think maybe on Wednesday, we may do a double sort of lecture, a little bit of lecturing during discussion, I think, as well. All right, any other questions before we wrap up officially the lecture portion here? Okay, I'll see everybody in a little bit. You know what? She just sent me the links to them. I'm not 100% sure what videos they go with or what labs they go with. The last I heard last week, they were a little behind, so I'm not 100% sure. So I don't want to say yes or no, but I'm just going to post up what she sent me in terms of the links. I think the labs you're supposed to maybe be working on this week, and I'll put that up right now in this little break time before I come back to discussion. Okay. All right, so I'm going to officially stop this one, I think. And I'll see you in discussion, or I'll see you Wednesday, whichever way you're doing it. All right. No, you don't have to. You're welcome to come. You don't have to. If I do lecture during discussion, it'll be up on Canvas, the lecture part of it. If you want to, you're more than welcome to come. You can come too. It's fine. All right. I'll see you in a bit.